Previously, we have seen that in a partially ordered set, that is, a set equipped with a partial order, it is possible for us to compare certain pairs of elements therein, pretty much as we compare the values of two real numbers. However, there is an important caveat that we should keep in mind. To see this, recall the two partial orders we have defined for the set of natural numbers. In the first case, a natural number x precedes or is equal to a natural number y if and only if x is less than or equal to y. In the second case, x precedes or is equal to y if and only if x divides y. We have already verified that both relations are partial orders on the set of naturals. However, there is a key difference between these two. In the first case, given a pair of natural numbers, say x and y, we know either x is less than or equal to y, or y is less than or equal to x. In other words, we can always compare any two natural numbers using this relation. However, if we now consider the partial order given by the divisibility and take x to be 3 and y to be 5, it turns out that 3 does not divide 5, neither does 5 divide 3. In other words, we are somehow in this awkward scenario that neither of these two elements is related to the other under the given partial order. Given arbitrary two natural numbers, we can always compare them using the first partial order, but not necessarily the second one. This motivates the definition of a total order, which is simply a partial order plus an extra property known as the totality. To this end, let us consider a partial order on the set A. Recall that this means a boundary relation on the set A that is reflexive, antisymmetric, and transitive. And now we say it is a total order if, in addition, for any elements x and y in A, either x precedes or is equal to y, or y precedes or is equal to x. This is known as the condition of totality. Intuitively, it simply means that we can always compare arbitrary two elements with this order. Very often, we will say that x precedes y strictly or simply x precedes y to mean that x is related to y under this partial order, but x is not equal to y. Hence, if the set is equipped with a total order, then for any two elements x and y, we will always have the following trichotomy, that is, either x precedes y, or y precedes x, or x and y are equal to each other. Clearly, by the property of a total order, all these three cases will be mutually exclusive. Now, let us revisit some of the partially ordered sets introduced previously and check if the partial order defined therein is indeed a total order for each of these examples. First, let us consider the partial order defined on the power set of N. We're given two arbitrary subsets, x and y, of the naturals. X precedes or is equal to y if and only if x is a subset of y. This partial order is not a total order. Now, if we take x to be the singleton set consisting of only 0, and y to be the singleton set consisting of only 1, we see that neither x is a subset of y, nor is y a subset of x. Hence, these two subsets are not related to each other. The totality condition fails here, and we conclude that this is only a partial order, not a total order. Next, let us consider the partial order defined on the product set n squared, where for any two arbitrary ordered pairs z1 equal to x1 y1 and z2 equal to x2 y2, we say that z1 precedes or is equal to z2 if and only if x1 is less than or equal to x2 and y1 is less than or equal to y2. This is the standard product order, also known as the coordinate-wise order. We have already verified last time that this is indeed a partial order. Now, let us take two distinct elements, where z1 is equal to 6 and 7, and z2 is equal to 7 and 6. Now, by comparing the second coordinate, we see that z1 does not precede z2. By comparing the first coordinates, we see that z2 does not precede z1 neither. Again, we're now in a situation where two elements are not comparable under this partial order. As a consequence, this is only a partial order, not a total order. Notice that although the standard product order fails to be a total order in general, it doesn't mean that we can never establish a total order on the product set. Actually, let us now define a new order on N2, where for two elements z1 and z2, z1 precedes or is equal to z2 if and only if either x1 is strictly less than x2 or x1 is equal to x2 And on top of that, y1 is less than or equal to y2. We now verify that this is indeed a total order on the product set. In other words, we should verify the reflexivity, the antisymmetry, the transitivity, as well as the totality. The first three conditions will guarantee it is a partial order, and together with the last condition, we will achieve a total order. Let us start from the reflexivity. Given an arbitrary z equal to xy in N2, since x is equal to x itself, and y is less than or equal to y itself, the second part of the disjunction is thus always true, and from there, we see that z is always related to z itself. This proves the reflexivity. Next, for the antisymmetry, suppose that we are given two elements z1 and z2, where z1 precedes or is equal to z2, and z2 precedes or is equal to z1. This translates into the following two conditions based on the definition of a binary relation. Now, let us consider three segments, which are x1 is strictly less than x2, x2 is strictly less than x1, x1 is equal to x2. Clearly, these three segments are mutually exclusive, and exactly one of them can be true. Thus, for both conditions to hold, the only possibility is that x1 is equal to x2. From there, these two conditions are now simplified into x1 being equal to x2 and y1 being less than or equal to y2, and x2 being equal to x1 and y2 being less than or equal to y1. Together, we deduce that x1 is equal to x2 and y1 is equal to y2. Since both coordinates coincide with each other, we conclude that z1 is equal to z2. This proves the antisymmetry. Next, for transitivity, let us assume that we're given three ordered pairs, z1, z2, and z3, respectively, where z1 precedes or is equal to z2, and z2 precedes or is equal to z3. Now, let us analyze these conditions. We see that for z1 to be related to z2, we must have x1 be less than or equal to x2. Similarly, for z2 to be related to z3, we must have x2 be less than or equal to x3. Putting them together, we now get a chain that is x1 is less than or equal to x2, which is in turn less than or equal to x3. If either of these inequalities is strict in this chain, x1 will be less than x3 strictly, and we're done. Otherwise, both inequality become equality, which reads x1 is equal to x2, which is equal to x3. In this case, both conditions are simplified into the second half, and putting them together results in x1 is equal to x3, and y1 is less than or equal to y3. So again, we will always have that z1 precedes or is equal to z3. This proves the transitivity. So far, we have already seen that this relation is indeed a partial order. To finish, let us show the totality condition. So let us take two arbitrary elements, z1 and z2, and compare first their x coordinates. There are only three possibilities. Either x1 is less than x2, in which case z1 precedes z2, or x2 is less than x1, in which case z2 precedes z1. In the third case, x1 is equal to x2. And then let us move forward to compare their y coordinates. And clearly, either y1 is less than or equal to y2, in which case z1 precedes or is equal to z2, or y2 is less than or equal to y1, in which case z2 precedes or is equal to z1. Great. So no matter which case we're in, we will always be able to compare z1 and z2 under this order. In other words, this is indeed a total order. This order is known as the lexicographic order. We use this name because the way how we compare two terms mimics exactly how we compile a dictionary. Imagine that we're given two English vocabularies. How do we determine which one shows first in a dictionary? Well, we will start by comparing the alphabet of their first letters. And if their first letters agree with each other, we then move forward and compare the alphabet of their second letters. If needed, we can keep going until a conclusion can be made. We leave it as an exercise to the audience to verify that the discussion here can be easily generalized. Indeed, if A is a set equipped with a total order, and B is another set equipped with a total order, then we can construct the lexicographic order on their product set A cross B, which will again be a total order.